Greetings, everyone! Welcome to today's presentation. In this session, we'll explore how GPUDirect storage, or GDS for short, integrates seamlessly with QSAN's XCubeNXT storage solution. In today's data-driven world, especially in fields like AI training, deep learning, and high-performance computing, efficient, low-latency data access has become a critical factor in overall system performance. GDS allows GPUs to access storage directly, bypassing the CPU, which helps eliminate bottlenecks and significantly boosts system throughput. When combined with the powerful architecture of XCubeNXT, it creates a solid and efficient foundation for accelerating enterprise data workflows. In this video, we'll walk you through the core concepts of RDMA and GDS, system setup and configurations, performance test results, and real-world application examples, so you can better understand how to leverage the solution to optimize your data-intensive workloads. In this presentation, we'll be taking a closer look at GPUDirect storage and how it integrates with QSAN's XCubeNXT storage platform. Here's what we'll cover today. First, we'll start with an introduction to RDMA and GPUDirect storage to help you understand the core technologies behind the solution. Next, we'll talk about how GDS is integrated with XCubeNXT and what makes it a great match for high-performance environments. Then, we'll dive into the system architecture, giving you a clear view of how the components connect and interact. After that, we'll share some performance insights, including key metrics and advantages you can expect. And finally, we'll wrap things up with a brief conclusion to summarize the value of this integration. Let's get started. Remote Direct Memory Access, or RDMA, is a networking technology that allows one computer to access the memory of another without involving the CPU or the operating system. It's widely used in high-performance computing and distributed storage environments where speed and efficiency are critical. Let's take a look at the key working principles of RDMA. First, RDMA enables direct memory-to-memory data transfers between nodes, a mechanism often referred to as zero copy. Second, during the data movement process, there's no CPU involvement, which helps to significantly reduce latency and free up processing power. Third, RDMA data transport can be carried out over InfiniBand ROS, which stands for RDMA over Converged Ethernet, or IWARP, depending on the infrastructure setup. These features make RDMA a powerful enabler for modern, high-throughput applications. First, RDMA eliminates the data copy overhead between the CPU and the operating system. In traditional I/O operations, data is copied multiple times between user space, kernel space, and the network interface. This process consumes significant CPU resources. With RDMA, data is transferred directly between memory locations, bypassing the OS, which improves performance and reduces latency. Second, RDMA takes advantage of hardware-accelerated transport capabilities. By using protocols like InfiniBand or RDMA over Converged Ethernet, RDMA leverages specialized network interface cards to achieve high-speed and low-latency data transfers. This makes the data movement much more efficient and reliable. Finally, in RDMA, the CPU initiates the transfer, but the actual data movement is handled by the DMA engine. This means the CPU is only responsible for triggering the operation, while the heavy lifting is offloaded to the network hardware. As a result, the system minimizes CPU load and avoids unnecessary OS intervention. GPUDirect Storage, GDS, is an NVIDIA technology aimed at optimizing GPU direct access to storage systems, reducing CPU overhead, and improving data transfer efficiency. Traditional GPU data flow. Application reads data from NVMe, SSD, NFS storage to CPU memory. CPU copies data to system memory. CPU sends data to GPU memory over PCIe. GPU begins processing. GDS optimized flow. GPU issues a DMA request. Data transfers directly from NVMe SSD or NFS over RDMA into GPU memory. No CPU memory staging. Faster data availability and reduced CPU load. The connection topology is quite simple. It involves establishing a direct high-speed RDMA, remote direct memory access, capable networking between the GPU server and the XCubeNXT storage system, with RoCE v2 RDMA over Converged Ethernet v2 being the preferred choice. This setup provides low latency and high bandwidth, ensuring efficient data transfer and significantly enhancing overall system performance. The use of RDMA technology facilitates direct memory access between devices without the involvement of the CPU, reducing overhead and boosting throughput. Reduced latency, the GDS technology minimizes intermediary steps in data transfer, leading to faster data delivery and significantly reducing latency. This is especially important for applications that require real-time processing, such as high-performance computing and deep learning, as it dramatically speeds up processing time and efficiency. Lower CPU overhead. Traditional data processing typically involves substantial CPU computation and data movement, but GDS technology enables direct data transfer between the GPU and the storage system, bypassing the CPU. This reduces the CPU's workload and allows it to focus on more critical computational tasks. Higher data throughput. With GDS, data can be transferred directly from the storage device to GPU memory, avoiding multiple stages of data copying and movement. This leads to a significant increase in data transfer speed, improving bandwidth and maintaining stable data flow even under heavy load. Enhanced overall application performance. By making the data transfer between the GPU and storage system more efficient, GDS technology provides significant performance gains for a wide range of applications, whether it's data analysis, machine learning, or image processing. As a result, applications can complete more computational tasks in a shorter time, leading to greater productivity. We compared the performance of GPUDirect storage, GDS, with traditional CPU-mediated data transfer. These represent different I/O architectures. Transfer Type 0, which is GDS, storage to GPU memory via RDMA, zero copy, CPU bypassed. Transfer Type 2, which is the traditional mode, storage to host memory, then to GPU memory via PCIe copy. Key observations. Block size matters 64. KAB block size provides the highest bandwidth and most stable latency. CPU utilization reduction, GDS transfer type 0, reduces CPU utilization by about 80 to 85%, freeing up more CPU resources and improving system efficiency. Steady throughput. Despite bypassing host memory, GDS type 0 achieves similar or better bandwidth compared to traditional methods, making it suitable for AI and data analytics workloads. The integration of GPUDirect storage, GDS, with XCubeNXT storage solutions delivers a powerful architecture tailored for data-intensive workloads such as AI training, real-time analytics, and high-performance computing. By enabling direct data transfer between storage and GPU memory via RDMA, GDS effectively eliminates CPU bottlenecks, reduces latency, and enhances data throughput. Key takeaways. Seamless compatibility. XCubeNXT supports NFS over RDMA, enabling straightforward deployment of GDS with minimal configuration overhead. Performance efficiency. Direct data path to GPU memory reduces CPU load, improves training speed, and increases GPU utilization. Validated architecture. Real-world test results confirm the robustness of the solution, with GDS delivering consistently higher throughput and lower latency compared to traditional I/O paths. Flexible deployment. The architecture supports various use cases from model training to large-scale data analytics, while maintaining scalability and cost efficiency. Enterprises adopting GDS with XCubeNXT gain a competitive advantage through accelerated data pipelines and optimized infrastructure performance. This solution not only meets today's demands for AI scalability and speed, but also lays a foundation for future growth in GPU-accelerated environments. By reducing data movement overhead and unlocking full GPU potential, organizations can streamline innovation and reduce time to insight in mission-critical applications.